Catholic University Santiago of Guayaquil. Danazol treatment for telomere disease. Student Andrea Bifarini. Definition: genetic defect is telomere maintenance and repair cause bone marrow failure, liver cirrhosis and pulmonary fibrosis, and they increase susceptibility to cancer. Histologic androgens have been useful and treatment for marrow failure syndromes, induced culture and animal models. Sex hormones regulate expression of the telomere genes. What is a telomere? Telomeres are repeat exact nucleus and associated proteins that are located at the ends of linear chromosomes. Ends from recognition as damage or infection DNA. The repair of telomeres by the telomerase complex solves the end replication problem. The other ways inhibit loss of genetic material with every cell division. Telomerase is active during embryogenesis and in proliferant adult tissues, for example, in hematopoietic system cells and immunocells.
Okay guys, this video is going to be about telomeres. And what is telomere? You know, telomere is a specialized structure of eukaryotic chromosome that is present at the terminal region of the chromosome. Or let's see here, in this picture, as you can see that these are the two parts called telomere, that is the end part of the chromosome, right? Because you know, eukaryotic chromosome is linear, because eukaryotic DNA is also linear, and to prevent that DNA from further damage, there is a specific structure at both the terminal of that chromosome. It is called telomere, and the structure that is present at this terminal region is having either formation of loops, or it can be it sometimes have the repeated sequences. As you can see here, the DNA that is present in the telomeric region has a repeated sequence, like, you know, GGGGTT, then GGGGTT, so like that, 4 G's then 2 T's, and that's how it's kind of repeated throughout the telomeric region. And it's a huge and long repeat of the DNA sequence that is present there, like that. Not only they have this repeated sequence, but also they have a loop formation with the DNA at the terminal of this repeated sequence. So this sequence is kind of fixed, but it is slightly varied between species to species. As you can see here, it is from the tetrahymena, and for human that is slightly different, but that's kind of thing, because they have a repeated sequence in all the different species. Okay, now the telomere is supposed to prevent the chromosome shortening. You know, chromosome shortening, so let me write chromosome shortening. Chromosome shortening is a phenomena during the replication of eukaryotic chromosome, and during the replication of eukaryotic chromosome, each time after each replication cycle, they lost a particular part of the telomere during each session. To prevent that from happening, there is a repeated sequence of the DNA, so that even though they lost some amount of chromosome from the terminal region, ultimately they have all the necessary coding region of the DNA present. Because if you look at here in this chromosome, you can find this dark blue color sections are there, and light color sections are there. Both of the sections are there. Now among them, suppose light color sections are the coding regions. So these are the coding regions. Actually all the necessary coding regions which code for proteins are present. But if you look at the telomere, there is no coding sequence present, because telomere is not somewhere which is responsible for producing proteins. It is only responsible for preventing rest of the coding and non-coding sequence of the chromosome, right? So that is what the function is. because even if you have lost some amount of telomeric DNA sequence from the end, ultimately it will not reach any of these coding regions, because the telomere is large and it is forming the loop with many different proteins to form complexes. It's a huge complex, and complete structure of telomere is not yet been depicted, but it's under the very, very high influence of research nowadays.
Methods. In a phase 1 to 2 prospect study involving patients with telomere disease, we administered the synthetic sex hormone Danazol orally at a dose of 800 mg per day for a total of 24 months. The goal of treatment was the attenuation of accelerated telomere attrition, and the primary efficacy endpoint was a 20% reduction in the annual rate of telomere attrition measured at 24 months. The occurrence of toxic effect of treatment was the primary safe endpoint. Hematologic response to treatment of various time points was the secondary efficacy endpoint. Patients 2 years of age or older were eligible for enrollment at the NIH Mark O. Hofstra Clinical Research Center. The entry criteria included an age-adjusted telomere length at or below the 1% identified mutation, telomere maintenance and repair genes, or both, plus at least one low blood count. Danazol. Oral administration of Danazol 800 mg daily divided into 2 doses per day was planned to continue for 2 years. The dose was reduced if a patient reported unsuccessful side effects, and treatment was discontinued entirely if any grade 3 or 4 adverse events attributable to the drugs occurred. Data of adverse events were collected in accordance with the National Center Institute Common Terminology Criteria for Adverse Events, version 4.0.
Anabolic steroids are man-made substances related to male sex hormones. Doctors use anabolic steroids to treat some hormone problems in men, delayed puberty, and muscle loss from some diseases. Bodybuilders and athletes often use anabolic steroids to build muscles and improve athletic performance. Using them this way is not legal or safe. Abuse of anabolic steroids has been linked with many health problems. They include acne, breast growth and shrinking of testicles in men, voice deepening and growth of facial hair in women, high blood pressure, heart problems, including heart attack, liver disease, including cancer, kidney damage, and aggressive behavior.
Results. After 26 7 patients were enrolled. The study was highly early because telomere attrition was reduced in all 12 patients who could be evaluated for the primary endpoint. In the intention to treat analysis, 12 of 27 patients, 44%, 95% confidence interval, CI 26 to 64, meet the primary efficacy endpoint. In aspect, almost all the patients, 11 of 12, 92%, had a gain in telomere length at 24 months as compared with B-cell. In exploratory analysis, similar increases were observed at 6 months. Hematology response occurred in 19 of 24 patients, 79% who could be evaluated at 3 months, and in 10 of 12 patients, 83% who could be evaluated at 24 months. Who could be evaluated at 3 months, and in 10 of 12 patients. Non-adverse effect of danazol elevate liver enzyme levels and muscle calm of rate 2 or less occurred in 41% and 33% of the patients respectively.
The ends of linear chromosomes pose unique problems during DNA replication. Because DNA polymerases can only elongate from a free 3' hydroxyl group, the replication machinery builds the lagging strand by a backstitching mechanism. RNA primers provide 3' hydroxyl groups at regular intervals along the lagging strand template. Whereas the leading strand elongates continuously in the 5' to 3' direction all the way to the end of the template, the lagging strand stops short of the end. Even if a final RNA primer were built at the very end of the chromosome, the lagging strand still would not be complete. The final primer would provide a 3' hydroxyl group to synthesize DNA, but the primers would later need to be removed. The 3' hydroxyl groups on adjacent DNA fragments provide starting places for replacing the RNA with DNA. However, at the end of the chromosome, there is no 3' hydroxyl group available to prime DNA synthesis. Because of this inability to replicate the ends, chromosomes would progressively shorten during each replication cycle. This end replication problem is solved by the enzyme telomerase. The ends of chromosomes contain a G-rich series of repeats, called a telomere. Telomerase recognizes the tip of an existing repeat sequence. Using an RNA template within the enzyme, telomerase elongates the parental strand in the 5' to 3' direction, and adds additional repeats as it moves down the parental strand. The lagging strand is then completed by DNA polymerase alpha, which carries a DNA primase as one of its subunits. In this way, the original information at the ends of linear chromosomes is completely copied in the new DNA.
Conclusion. In our study, treatment with danazol led to telomere elongation in patients with telomere disease. Thank you.